Hi, this is Dong Lao from UCLA. In this video, I will show you our latest progress on atmospheric turbulence mitigation. This work has been conducted in UCLA-Vision Lab under the supervision of Professor Stefano Soato and in collaboration with Conley from Berkeley and Alex from Yale. Given multiple turbulent images captured from a static scene and a static camera, we aim to recover the underlying scene free from turbulence. This task is crucial in computational imaging, as atmospheric turbulence is everywhere, from a hot barbecue grill to astronomical telescope imaging. Our interest in this topic stems from the UG2+ challenge at CVPR 2023, and this paper is an extension of our challenge submission. We appreciate the organizers, and we are also honored that our paper has been selected as a highlight paper of CVPR 2024. As you can imagine, this task is quite challenging due to the difficulty in obtaining ground truth training data. So, instead of designing a new learning scheme, we went back to the fundamental principles to see where we can improve. Here is an overview of most of the existing methods. Given a sequence of turbulent images, the goal is to register each image to a distortion-free template of the scene, and then integrate these images to reconstruct a clean image. Various techniques, such as blind deconvolution or deep learning, can be employed for this purpose. Let's first focus on a liberation assumption, where all inputs IETs are obtained from the same ground truth scene with a diffeomorphic deformation and some imaging noise. Diffeomorphic here means there's no occlusion induced by motion. The turbulence removal problem can thus be framed as a reconstruction problem. If we assume Gaussian imaging noise, by variational calculus, we have an explicit solution. We can see that the key here is to estimate this deformation W. Returning to the diagram, we need to estimate the deformation from the template to each image, which often requires an initial template. Typically, people use the average of all inputs as an initialization, which can lead to a blurry template and inaccurate registration. The question then is, can we improve this process? The rationale behind using average is that, without any prior knowledge of turbulence, it is fair for people to just assume that the deformation is zero mean, so their average converges to zero. We parameterize deformation by an optical flow field. Interestingly, the flow from the template to the target frame can be decomposed into the flow from the template to an intermediate frame, and the flow from this intermediate frame to the target frame. We call this intermediate frame the key frame. Combining this flow composition rule with the zero mean assumption allows us to estimate WK in this manner. This formulation is noteworthy because WK is computed only from the flow from the key frame to other frames. So it doesn't need an explicit template to estimate the deformation of the key frame. Remember, now we have one explicit solution, we have the flow composition rule, and we have this formulation. If we combine them together, we developed a solution for the turbulence removal problem. This solution allows us to register each input image to the template without actually using the template. Thereby, we bypass the issue of an initial blurry template. Everything looks promising so far, except for one challenge. Our formulation requires inverting an optical flow. This means, given the flow from A to B, we need to estimate the flow from B to A. Since there is no explicit solution, we hard-coded a solution using interpolation and inpainting, which is another contribution of our work. Detailed explanations can be found in the paper. Now, let's look at some results. We simply choose the first frame of each sequence as the key frame to demonstrate the robustness of our framework. You can see that our registration scheme improves the quality of the template, resulting in a more rigid and clear outcome. We integrated with downstream pipelines. Our results appear sharper. If we zoom in, you can notice significant improvement in the fine details of the reconstruction. This is validated by numerical evaluation. We also found that our method is not sensitive to the choice of the keyframe. Interestingly, while the quality of the template quickly saturates with averaging, our registration scheme continues to improve as more frames are added. We hope you enjoyed this video. There are certainly future extensions to consider, such as better flow methods, a learning-based registration pipeline, and adapting the model for dynamic scenes by dropping the zero-mean assumption and integrating any motion prior. If you have any further interest, please contact me via my email. Thank you.